Good evening. So I'm going to be talking about earthquakes and tsunamis in subduction zones. I'm going to focus on shallow, slow slip. I'm going to try and talk a little bit about marine geodesy and how that can help us understand the processes that go into shallow, slow slip. So the earthquakes and tsunamis that happened in 2004 in Sumatra and 2011 in Japan were really wake-up calls that we needed to do a better job of forecasting these events. We have a simple model for how these earthquakes and tsunamis happen. Basically, we have a long period of interseismic strain accumulation due to the locked plate boundary. And then we have a rapid period of strain release, which causes the earthquake and the tsunami. The size of the earthquake that comes out of this process is related to the area of the patch that slips and the displacement on that patch. And both of those are in principle measurable with geodesy. So slow slip events are similar to earthquakes, except they're slower. They release energy over weeks or months. But if you have enough of them, they wind up limiting the subsequent area of co-seismic rupture. So that's an important point that I'm going to be focusing on in the next few slides. We were able to test this concept pretty nicely in Costa Rica a few years ago. The 2012 earthquake that Thorin Lay talked about last night was nicely surrounded by areas of slow slip. So that's an important observation that we'd like to test. It's happened elsewhere. Here's an example from the Bozo Peninsula in Japan, where we have several shallow, slow slip events, and they're always accompanied by earthquake swarms, but the earthquakes are always down dip of the shallow, slow slip. A similar pattern is observed by my colleagues Jean-Mathieu Noquet and Patty Mothez and others in Ecuador. They have also demonstrated that shallow, slow slip brackets the area of subsequent co-seismic rupture. It is also found in Nankai, where low-frequency earthquakes, the yellow and red colors, which are basically a proxy for shallow, slow slip, occur up dip of the rupture area of the 1944 Tonankai earthquake. So the questions are, do slow slips always bracket subsequent co-seismic rupture, or is that only true some of the time? Can we distinguish when it's true versus not true? And can we use this information to help us forecast? We know that things change over time. The top panel is a long-term record for earthquakes in Cascadia, and the lower panel reminds us that in the 2011 earthquake in Japan, the earthquake ruptured a much larger area than previous events. What's going on? So I think shallow subduction zones are a key part. That's where diagenesis happens. That's where fluid flow happens. Cork data and other data suggest that the fluid flow is variable, and that implies that the frictional conditions are also variable. The standard model for the subduction interface emphasizes spatial variability. So we have patches that occasionally rupture in earthquakes, and the size of the patch is related to the size of the earthquake. What I think we need to do is add time variability to this model and measure it with something. Shallow, slow slip events are a key part of the story because they release some fraction of the accumulated strain, and they indicate special frictional conditions, and those frictional conditions can change rapidly. To do those measurements, we need better seafloor geodesy. We need better time resolution, we need better accuracy, and we need to get a lot more data, which implies that we need cheaper seafloor geodetic methods. There's two areas to consider, deep water and shallow water. In deep water, I think the answer is pressure gauges, but I think we need to do a better job of calibrating the oceanographic effects. In shallow water, it's a little bit more complicated. We lack good tools for doing shallow seafloor geodesy, but it's an important region. Here's a bathymetry chart of the Cascadia margin. The shallow water is in orange and yellow, and there's basically 25 to 30% of the real estate between the trench and the coast that's at that shallow level. So that's an important area that we need to emphasize, and we can't really do it right now. There is a possible tool that will work. It's basically a heavy-duty GPS buoy. The Italians have developed this system, and they use it to measure vertical to 1 centimeter. If we simply added tilt meters to this system, we could get the horizontal to 1 centimeter as well. We've been working to develop this. We have the different parts that are almost ready to be hooked together, and we hope to put it in the water this summer. Thanks very much.